thanks for inviting me. Thanks for showing up. It's a nice little group, little different audience that I'm used to. I'll do my best to get not too technical, not too many difficult jargon words. If there's anything where you have questions, just feel free to interrupt me. So yeah, I'm a paleoclimatologist, also paleoceanographer. So paleo, just for context, paleo from Greek means old or past. So I'm basically studying the past climates and the past oceans. And we do that because the advantage of the past is it already happened. So we can actually study climate change and changes in the oceans that happened in the past. And then when I'm talking about the past, I'm talking about the last couple of 100 years, 1,000 years, even back to millions of years. So the topic depth applies actually to two different connections to my work. That's, as Charlotte said, the deep ocean, but it's also what we call deep time. So when we talk in our field about deep time, then we are really thinking of millions of years back into the past. Now, before I talk about this and how we do that, I want to start actually a little bit with the motivation of our work, and that is obviously also what's going on right now and what is going to happen in the future, because eventually we want to understand better what is waiting for us. And a lot of these issues are, I guess, familiar to you. So what we see here is basically the problem of global warming. So you will see quite a few of these types of slides, so you get used to it. So we're having here a time series. In this case, we're going back the last 60 years or so, and these are the measurements of atmospheric CO2 concentrations as they have been started on Hawaii. Atmospheric CO2, that is actually causing, of course, modern global warming. And you see we're now at around 420 ppm. And we started at the start of the Industrial Revolution of something like 280. And what I plotted in here also are the moments when we had these big climate conventions, which sent out a really positive signal. And you see the effect of those so far was rather limited. Also here, maybe you have, if you think we had this thing called COVID in 2020, we flew a lot less. We were commuting less. And the emissions actually reduced by something like 7-8% globally, but still, if you look at the total trend in CO2, not much happening yet. So this is causing, through the greenhouse gas effect, global warming. And another slide, I hope that's also visible for you. So this is from the IPCC. I guess many of you have at least heard about that. That's this kind of UN convention of climate scientists. They meet every 5 to 6 years, review all the literature on global warming and climate change, and then assess this and come with an assessment report. And that was the last report from last year, and there's really no debate anymore, so that is really clear now. Global warming is happening, so this is the temperature deviation with respect to pre-industrial, so 1850 over the last 2,000 years. So you see over 2,000 years temperature was relatively stable, and then over the last 100 years or so we have this rapid increase. We're now round about 1.1, 1.2 degree warmer than we were, let's say, 100 years ago. And it's also absolutely clear that this is because of this increase in atmospheric CO2. Right? That we really, you should never, in science, you should never talk about 100% sure, but it's getting very close to 100%. The question, however, is, there's many questions, but it's basically, the climate system hasn't responded entirely to this forcing. It's a bit like if you stand up in the morning, you turn on the radiators in your house. Radiators are warm, but the room isn't warm yet, right? It takes some time, a couple of minutes, hours, depending on your house, until it actually equilibrated, as we speak of, to the heat that comes off the radiators. And similar thing is happening also with the Earth, but then on very long timescales. So we turn on the heater, that's the CO2, and now the Earth warms and warms, and the question is, when does it reach equilibrium? At which temperature increase? Another problem that is related to this, and this is actually science that came out just a couple of weeks ago, a new nice, or actually horrible summary of what could happen. We're talking about these tipping points in climate. So things do not go gradual, but once you reach certain thresholds, developments increase and the rapidity of change increases. So what we know is that there are many of these tipping points in different aspects of the climate system or the Earth system, and we reach them under certain amounts of warming, global warming. So, for example, when we reach something like 2 degrees, the West Antarctic ice sheet starts to collapse. The Greenland ice sheet starts to collapse. When we reach 2 to 4 degrees, Amazon rainforest starts to die back. Things like boreal forests change rapidly. If we reach more than 4 degrees warming, the East Antarctic ice sheet starts to collapse. This is obviously happening on longer timescales, but it's then we reach moments when these systems just start going and they won't stop, and when these ice sheets all collapse, then we're talking about sea level change on long terms, several hundred years, of course, but sea level change of, in total then, 60, 70 meters. So if you would stand on the top of the Utrechtse Heuvelrug, you would just have dry feet, but everything around you would be covered in water. So this is really the most extreme scenarios. But these tipping points we have to keep in mind, and also when we think about future warming, when do we cross them? So there are also some projections in this latest IPCC report, and this is what the future could look like under different, what is called shared socio-economic pathways. So this is actually a relatively new thing in IPCC. In the past, it was the predictions were based on certain amounts of emissions, leading to a certain amount of warming. What they include now in the IPCC are really narratives of how society responds to changes or how society develops, and depending on this, or these narratives are associated with a certain level of warming. So this is actually 3 of the 5 scenarios. So you could say we are now here, around about 1 degree warming with respect to pre-industrial, and these are the next 200 years or so. Depending on these scenarios, we either stabilize, we have a few more degrees warming, or this is typical called the worst case or business as usual scenario, then we're going to something like 9, 10 degrees warming. Now, if you think about the tipping points that I just showed, all of them are basically crossed at 4 degrees already, then we should really, really avoid this. So there's a little bit of text, and I'd like to read that, and you can guess which narrative, which scenario this one is. So I'll read that out. So this is one of those socioeconomic pathways. So in this particular pathway, the world places increasing faith in competitive markets, innovation, and participatory societies to produce rapid technological progress and development of human capital as the path to sustainable development. Global markets are increasingly integrated. There are also strong investments in health, education, and institutions to enhance human and social capital. At the same time, the push for economic social development is coupled with the exploitation of abundant fossil fuel resources and the adoption of resource and energy-intense lifestyles around the world. All these factors lead to rapid growth of global economy, while global population peaks and declines in the 21st century. Local environmental problems like air pollution are successfully managed. There's faith in the ability to effectively manage social and ecological systems, including by geoengineering if necessary. What do you think? Which pathway is it? What does it sound like? Well, this is the description of the worst case scenario.
Really? Yeah, of course, it's gross.
And exactly. So it's the key sentence is really here, coupled with the exploitation of abundant fossil fuel. This could also be in the party program. I don't mention any names, but you can think of quite a few, many of whom are in power worldwide. But this is kind of a scenario that a lot of people would think, okay, this is the way we're going for, right? And we certainly should not. This is problematic. And as I said, there's of course many things in here, in the mix, that we think, they're positive. Okay, local problems, air pollution, we have more filters and so on. But the key problem is really the abundant fossil fuel resources. That is part of this scenario, and that should really be avoided.
Isn't it always also the rapid growth of this global economy?
Well, that's a whole topic on its own, but there are examples where you can have economic growth without additional fossil fuel or exploitation of fossil fuels. But in most cases, it's true what we see in the past, that economic growth was almost everywhere globally connected to more fossil fuel usage. Okay, but this is one side of the story, obviously, and that's a very important one. How do societies respond to that situation? The other, and you could say this is the uncertainty in the future. The other uncertainty, and I don't go into all the details of that slide, but it's this term, and that is what people are, colleagues in my field are after. It's the so-called climate sensitivity. And this is the number that I was mentioning before. If you turn on the heating, increase CO2 in the atmosphere, how much warmer does it actually eventually get? And this is what we call equilibrium climate sensitivity. And that number that we're after, it's quite sad. That's the main key of my work, is basically getting the result of one number. Is the warming that is associated with the doubling of CO2 in the atmosphere. So as I said before, we were at 280. Let's say we get to 560 ppm at some point. How much warmer does it eventually get? And you can study that in different ways. So one way is to look at climate models, and all these dots here are different climate models, and you see a large variability. So some models predict, well, it gets warmer by 1.8 degrees globally. Some other extreme models say 5.6 degrees. So there's also large uncertainty on the, let's say, physical side. And we want to better constrain this uncertainty. What we actually want to know, does it warm a lot when we double CO2, or are we actually relatively close already here?
Did the uncertainty decline over years?
Well, that's a good question, and this is actually what you see also here in this. So this is the last IPCC report. This is the previous one. The models get more complex. They are better in simulating the response of clouds and so on, but with increasing complexity, the spread also increases.
What are the sources of those models? Are they all sort of serious sources? Like where the 1.8 comes from?
Well, it's different. This is models from, no judgment here, but by chance, that is actually a Russian model. But so there is, it's different groups worldwide. There's different climate models. These develop over years and decades. It's very complicated code, working with physical principles essentially, but because the climate system is so complex, it's not a simple equation. There's lots of factors, and that actually, and the more factors you include, the larger the uncertainty gets. But we have, and this is actually what we do, ways of constraining that better. And this is basically by looking at real data. And this is what I do. So I don't use climate models. So this is what my workplace looks sometimes like. We go out into the sea, research expeditions. This is actually an expedition I did a couple of years ago, crossing the Atlantic, actually coming from the Bahamas, going all the way to Ireland. This is in the area of Newfoundland, waves up to 5-6 meters, so we couldn't do a lot of work there. We're just trying to survive, basically. But sometimes the conditions are also nice, and then we can do a lot of things in the ocean. We can do a lot of measurements. And these are some of the instrumentation that we use there. So we have here what is called the CTD, so you do measurements in the water column. You can measure the temperature, salinity, pH, all kinds of things. We use these plankton towers, so that's basically nets that we use to fish stuff out of the water, and then we're not looking after actual fish, but little microorganisms. And with these instruments, we can take samples from the sea floor, so sediments that are sitting there in a few thousand meter water depth. And we're also taking these longer sediment cores where we actually start to drill into the ocean. So if you use these plankton nets, it's actually really fascinating what you get out there. There's a whole, huge variety of ecosystems everywhere in the ocean. It's not just a big empty bathtub, but depending on where you are, you always find new species and new ecological niches. But the nice thing is that many of these organisms, like these pteropods, little shells, we find them also back in the sediments. So by studying them in the modern realm, we understand how they respond to certain environmental conditions. And when we find them then back in the sediments that are hundreds or millions of years old, we can actually say something about the past. There's other drill ships like this. It's the famous JOIDES Resolution. It was actually I think 2 years ago in Amsterdam, actually in the harbor for some renovation. It's really the workhorse in terms of scientific ocean drilling. I was also joining one of the expeditions of the JOIDES a couple of years ago. And the specialty of that drill ship is really to take long drill cores out of the seafloor. So we can really drill hundreds of meters deep. And then you get sections of something like this 10-meter long cores. They get on board. We cut them into meter-long sections, open them up, and then they look like this. And you see all these layers here already appearing. And basically, when you go from the sea floor down into the sediments, you come across older and older layers. It's like that's what we use as climate archive. So when you go a few centimeters, you go back a few hundred years. If you go meters, you start looking back 10,000s and 100,000s of years. If you have hundreds of meters, you're going back millions of years back in time.
Is that new ocean sediment? They used to take only ice to find things.
I would say that ice is relatively new. New, speaking of the last 30 years, but sediment cores are being studied since, the 1960s, really, it started.
How does the technology roughly work to make these drills?
Yeah, it's actually pretty mind-blowing. So there's lots of metal pipes here on board, kilometers of metal pipes. They are put together and then piece by piece lifted up into this rig and then lowered. So once you actually on location, you have the ship there, and up to 5 or 6 kilometer long metal pipe hanging under the ship. And in that metal pipe, you actually have the drill bit, and then you take a 10-meter piece out of the sediment floor, you bring it up, you make the pipe a bit longer, and then you take the next 10 meters, and that way you can drill hundreds of meters into the seafloor. This is also how they actually drill for oil, but they're not interested in the sediment, they kind of chuck it away. And we're not interested in the oil, but we are interested in this. So, but yeah, so this is yeah, this is what one of these core sections looks like. So if you would stand here, if you would imagine this is the sea floor, you go into the sediment. That's different components that accumulate there over the years. Let's say this could be the last 10,000 years or so. And these color changes that you see already, they already represent climate change in the past.
So how much kilometer of drill is this?
So this is just 1.5 meters in that case. Just one piece of the core, and you could make that a couple of 100 meters long.
And this is 1.5 meter, and what is it in time?
That depends, of course, on the sedimentation rate, so the accumulation of material, and that depends on the location. So there's some locations in the North Pacific where we have per year or per 1,000 years something like 1 to 3 millimeters. Very, very little, almost nothing gets there. There's other locations where you can accumulate up to 50 centimeters in 1,000 years. So in this case, that is actually from the Sea of Japan. We have sedimentation rates of something like 10 centimeters per 1,000 years, so that could be something like.
How do you know?
Yeah, so you date. There's different methods. That's a good question. There's different methods to date this. There's radiometric methods. Said I didn't want to go too technical, but you can measure the ratio of certain radiometric or radioactive elements. Radiocarbon, for example. There's others. Radiocarbon works for the last 70,000 years. There's other uranium, thorium. There's different methods that you can use to date these things.
So the same way as on land, it gets every year a new nuclear there.
Well, the thing on land, what is happening on land is that you accumulate, for example, if you go to a river system, you accumulate sediment, but there's always also continuous erosion. Yeah, so on the seafloor, the nice thing about the seafloor is you get deposition, but there's no erosion. So you have a nice continuous record that grows and grows and grows.
Unless there's an eruption, volcano.
Yeah, but we're going to places where that is not happening.
Tectonic plates.
Yeah, but exactly. Yeah. Mid-Atlantic ridges. But we're going to we do a lot of what we call site surveys. So
We're next to the place. We're not
exactly. A nice calm place, ideally where there's a lot of accumulation, so we can get a good sense of time. Speaking of time, I should make over here. So the other thing is, if we look at these sediments now, these sediment cores, and I actually forgot, I brought something with me. Precious sample from a sea floor, a sample that's a couple of million years old. So if you look at these sediments, if you wash all the really fine stuff away, this is what you get. Looks like sand, and if you put this under a scanning electron microscope, you actually see this. So this is what you have in that jar. It's little, what we call foraminifera, tiny little shells, actually plankton, animals, indeed zooplankton that floats in the sea. They're tiny, so here for reference, a little needle with one foram in there, and you see them there. So they build little calcium carbonate tests, like an oyster or a chicken egg or the scale in your water cooker, calcium carbonate. And we can measure now the composition of this calcium carbonate, the chemistry of it, the isotopic composition. And we know that under different temperature conditions, the chemistry and the isotopic compositions of these little shells changes. I'm not going into the details, but this basically gives us a thermometer. So under cooler conditions, basically the atoms and the isotopes within that shell have a different configuration. So if you give me, for example, the chicken egg that you ate this morning, I can measure the composition of isotopes in that, the ordering of isotopes in that shell, and that tells me something about the body temperature of that chicken when it produced the egg.
You also know the CO2 concentration there?
There's different methods that you also can say something about CO2 concentration, absolutely. In my own work, I focus mainly on temperature. So I try to reconstruct the temperature of the past. So yeah, I'm not going into but this is sort of the crystal structure of one of these calcium carbonates. And basically what we have means of measuring the ordering of isotopes in these crystal structures. And this ordering tells us something about temperature of the past. Okay, so we have a thermometer now, yeah? If I have one of these foraminiferas, or many of them, and I know they are 10,000 or a million years old, I can measure the temperature of the past, right? The question is now, how do I get the average temperature of the planet? That's actually also quite a difficult task, right? If you wanted to measure the average temperature of the planet today, where would you go? You would probably think all of the places, right? You would have to measure the temperature everywhere and then average it. So the modern average temperature of the planet is actually, any guesses? What do you think? What's the average temperature of
10
the...
degrees?
10 degrees, pretty close. It's actually around 14 to 15 degrees. So this is like a pretty average temperature for our planet right now. I don't know, but it is, maybe it's a little bit cooler.
Day and night included.
So including Antarctica, including the tropics, all the seasons, day and night, average.
Is it helpful to know the average? Because the impact is anyway always...
That is true. In the end, for your daily life, you're more interested in what's going to happen with the temperature in Utrecht.
The real impact, huh? Because maybe we keep it at 1.5 degrees, but still it may be 70 somewhere else anyway. So is it good enough to know the average temperature?
Well, yeah.
Sorry.
Yeah, no, so it is when we're talking about the average temperature, gives us a means to basically talk about the overall average impact.
So it's a safe range.
Well, it's a good metric to understand what is going to happen on average, right? And there are, of course, different impacts in different places, but typically if the temperature changes with 2 degrees on average globally, then I can sort of predict what is going to happen locally. Put it very simply. But yeah, absolutely, I don't know who said it, but you have to go to all places basically to average. And this is what we've done, or what also colleagues have done, for example, this situation, that was 20,000 years ago. That was during the last glacial maximum. So the last ice age. The whole of the northern hemisphere, or the large parts of the high latitudes in the northern hemisphere, were covered in a huge ice sheet, larger than what we have on Antarctica today. Here in the Netherlands, we were just at the margin of that ice sheet. So again,
And there was an atmosphere.
there was an atmosphere, yeah. And it was, in terms of atmospheric CO2, it was quite a bit lower than sort of half of what we have today. So if we want to get the average temperature of that planet, we go to many places and do reconstructions and average it all. So all these dots represent sediment cores, and where reconstructions have been in time, done in time, and then they were all averaged and compiled with the model, and then you get a temperature curve that looks like this. So now we're looking here at the last 20,000 years. This is actually the last 2,000 years sort of blown up. That's what we looked at before, very stable. And then we have here our modern warming, which is 1 degrees. When we go to the last glacier, we have a cooling globally of around 6 degrees. So this is what the doubling of CO2 did on this time scale. 6 degrees change and a huge increase, or in that case, decrease in the amount of ice on the northern hemisphere. If we want to go further back in time, this approach, getting all kinds of temperature estimates from around the world, is getting really difficult because we don't have that many locations. The evidence is getting sparse, so that makes it really complicated to reconstruct temperatures 1 million years or 50 million years ago. But we need to do that, actually, because the variability globally is so large, right? Some places are really hot, some places are really cold, so you need this average. So how can we solve this? And this is where the deep sea comes in again. So we go to a place that is really boring in terms of temperature, and that is the deep sea. So what I have here is the temperature, and I don't know if this is really visible, but the temperature of the sea floor in the modern realm. Here's a temperature axis, and you see that the warmest temperatures, we find them here in the Mediterranean and the Gulf of Mexico, but the big oceans overall are very boring, very similar. It's basically everywhere cold. So that means once you know the temperature at one of these locations, or a few locations, you can basically extrapolate and say, well, I know the temperature for the entire deep ocean, because there's not much variability. And the other useful thing is, once you know the temperature of the deep ocean, or temperature change in the deep ocean, you can easily extrapolate that to the average temperature of the entire planet. And that is because the deep ocean is such a big heat reservoir, it basically represents the change on long time scales in terms of the global surface. And this is this relationship. So we have here global deep sea temperatures in degrees. We are now somewhere here, so the deep ocean is very cold. Surface is around 14, 15 degrees. If we warm the planet, we warm the deep sea in a similar fashion as we would warm the surface ocean. So that means if we can reconstruct the temperature of the deep sea in the past and changes, then we have a means of reconstructing the global temperature change at the surface as well. So the nice thing is, going back to our sediment course, in this sample, which, I don't know, disappeared now, we still need to work on this. There's not only little forms that floated in the sea, but that actually also live on the bottom of the seafloor. So when we measure the temperature of those guys, or the temperature at which they precipitated, we know the temperature in the deep sea. And why do we want to go back very far, sort of into deep time? Because when we go millions of years back into time, the planet looked actually really different. So this is an example from the Baffin Bay in northern Canada, today completely covered in ice. And this little helper here holds up a picture that sort of shows the Baffin Bay something like 50 million years ago. It was a swamp. We find in the sediments, we find back palm tree pollen. So we know it was a very different planet then. It was very warm back then. And the reason for this warmth was high CO2 concentrations in the atmosphere. So another time scale. So what are we looking at now? This is CO2 concentrations, but now going into deep time. So again, this is the last 2,000 years. We came from something like 280 ppm. We are now at 420. These are our different economic pathways. So this was the worst case Feifei Day scenario. No, I shouldn't say that. This is sort of the worst case scenario. Going up to 2,000 ppm. Hopefully we manage to stay on track of one of those scenarios. This is when we go back into the past. So the last million years here, This is actually from the period where we also have ice cores and CO2 estimates from ice cores. Glacial, interglacial cycles between 100 and 280 ppm. And this is now the time axis is changing again, millions of years back in time. And you see that the CO2 concentration was a lot higher when we go into these past geologic periods. So 50 million years ago, we were somewhere around 1500 ppm, very high CO2 concentrations. So we can take now some of these anchor points and look at the temperatures, right, back in the past to get an idea of how much warming do we actually eventually get under these concentrations. So we have pre-industrial 280, that's our 0 point. We have the last glacier that I showed before, 180 ppm concentration. We saw that the cooling was something like 5 degrees, 6 degrees with respect to modern. Then we can go back to the period that's called the Pliocene, 400 ppm. So back then it was similar to what we have today. The Miocene, sort of an intermediate scenario for the future maybe, 650 ppm. And the early Eocene, 1500 ppm, sort of the worst case scenario. And what do our deep sea temperatures look like now for the same time period? Which will give us a flavor of what the surface temperature, how the surface temperature changed. So again, we are now here. This is modern. We're going back 65 million years. And if you look at these dark dots, these are our reconstructions of deep sea temperatures through time now. Today we are close to 0, something like 2 degrees. When we go to the Pliocene and Miocene, you see that the temperature increases to 10 degrees. And if we go to these very high CO2 scenarios, the temperature increases up to 17, 20 degrees in the deep sea. So it was extremely warm back then. No wonder that there were palm trees in the Baffin Bay. We can now plot these two things against each other, so CO2 versus temperature change. And then we get this relationship. So CO2 now on a logarithmic scale, temperature increase with respect to pre-industrial here, and we see a really nice relationship throughout the last 65 million years. 6.5 degrees. So actually we are on the very, if you look at the paleoclimate data, we are on the very high end of the model estimates. Right? That means that the climate is actually very sensitive to increases in CO2.
What was the reason of the previous concentrations? Natural cycle?
Yeah, it's natural variable. So on these long time scales, there's obviously the system Earth has ways to what we call sequester. So take CO2 out of the atmosphere and store it. So basically all the gas and the oil that we burn was previously also carbon that was in the atmosphere, but was taken out by, for example, the biosphere and sequestered in the Earth, basically.
Why did it get up?
Why it went up in the first place? Yeah, because also naturally these things can erode. It also depends on really tectonic timescales, how mountain ranges are built. So there's different ways to get naturally CO2 into the atmosphere and out of the atmosphere. Obviously the timescales are a lot longer than what we're seeing today. But sort of to take two conclusions, Earth past was actually warmer than we thought before, based on our latest evidence, and that means that if we take together climate model, CO2 reconstructions, and deep sea temperature data, they indicate what we call high Earth system sensitivity, so very high response in terms of temperature to a doubling of CO2. What does that mean for now? So we are here now. Yeah? We warmed the planet by around 1 degree. We are already at 400 ppm, a bit more, and I said that we're not in equilibrium yet, so the Earth still has to pick up. So if things go like they did in the last 65 million years, we would expect that sooner or later this is going to happen, that we shift to here. 4 degrees warming, if we further add CO2 to the atmosphere, it would get warmer and warmer. So when you think about our tipping points that I showed before, and when you think about this warming of 4 degrees, that would mean if we really get there, we basically have them all covered, right? We would cross them all. This is sort of at 4 degrees, all these systems would tip. Now there's also good news, so I don't want to send you depressed into the weekend, right? So this would happen if we keep CO2 concentrations in the atmosphere constant. And just wait. Or, of course, if we further increase CO2 in the atmosphere, it will get even warmer. However, what will actually happen once we reduce our emissions to zero, if we really don't add any CO2 to the atmosphere at all, the natural carbon cycle will actually start helping us. So in the way that in the past CO2 has been removed,
Because of the higher concentrations, it goes faster.
well, it doesn't necessarily go faster, but there are processes that will sort of will start to take CO2 out of the atmosphere again. So once we don't emit anything anymore, we will see that CO2 will slowly start to decrease. At the same time, the ocean is taking still up a lot of heat. So that means once we don't emit anything anymore, the temperature will stabilize pretty quickly. If we keep the concentration stable in the atmosphere, which we would do if we reduce the emissions by something like 60%, warming would continue. Probably even up to 4 degrees. So the task is really to get to net zero. It's basically, that is the big challenge. But as I said, the good news is that it's really still possible, right? It's not, so sometimes it's kind of the last stage of climate denial. We can't do anything anymore. It's over. It's already too late. That is not true. That is absolutely not true. As soon as we get to net zero, the warming will stop, and over hundreds of years, actually, it will probably at some point start cooling again.
Net zero in 2050?
Well, if we wait until 2050, it will still get warmer up until then, right? So as soon as we get to zero, it will stop. If we stop now emitting CO2, maybe a bit unrealistic, but warming would quickly stop.
We cannot allow overshoot because then you have the tipping point.
That's the other thing. If we wait for too long, we don't know how the first tipping points will come in and if they will actually accelerate the warming. Exactly.
Melting of the permafrost.
For example, yeah. So there could also be tipping points in the natural carbon cycle itself that actually nature will start to pump additional CO2 and greenhouse gases into the...
Good news is the methane, of course.
Methane is another greenhouse gas. Yeah.
What's the good thing about methane? You could explain maybe better, right?
No, there's no good thing about methane, but methane is a very strong greenhouse gas. So if we are also emitting that, but so...
We found out that the methane currently adds to 80 times than CO2. So if we reduce methane now, it helps a lot with the cooling. We didn't know that in advance because when we started climate change policy, we thought, well, it takes 100 years. But now we realize if we reduce methane now, it helps a lot.
Yeah. So these numbers that I use, they are sort of CO2 equivalents. So there's different greenhouse gases. CO2 is one very important one. Methane is a very strong one, but at the same time we have also very low concentration of methane. So, but this is kind of the total greenhouse gases together. But yeah, with that message, I really want to finish that presentation and hope that inspires you to to contribute and come up with the solutions, because I think in terms of science we know now really a lot. The challenge is really to get to one of those socio-economic pathways that reduces our emissions as quickly as possible.
Is there anything you still want to know as a scientist? What do you want to know?
Yeah, so this is of course the sort of simple version of the whole story, right? If you've seen the temperatures there's still a lot of variability, also in terms of the models. When we look at the model spread, we want to understand why is one model closer to, what does the model do better when we compare it to our data. And what you asked before about, this is about the global temperature, what is actually happening in terms of local variability. How do seasonal changes, how do heat waves change under, let's say, 2-3 degrees warming? So this is also things we study, and that are quite uncertain still.
You talked about, I think you see it in the news, there are tipping points for the worse when we are basically fucked. Are the tipping points feasible for the better? So now we reduce CO2, we do it very sort of linear, or
Yeah.
nice if we did it. Is it feasible to have a tipping point where we change everything for the better in a big step?
So better in the sense that it will then start to rapidly cool. Is that what you mean? Yeah.
Basically, be able to regulate it more. That would also be an interesting scenario.
So, well, the tipping point would be really the net emissions that we have. So as soon as we get to zero, we won't have any additional warming. I mean, some of those tipping points, you can have an argument. It's like a political argument. Then, is it actually getting better? Because if for example, the Sahel or southern parts of the Sahara start to green, locally you could argue, well, for people there it's maybe better. If you can start to do agriculture in northern Canada, where it's not possible now, you could argue maybe that is better. But all these changes are going on rapidly. So typically, if you look at the past, that is for human populations never really a positive thing. So
You say that the ocean is better in grabbing CO2
yeah.
if it heats up. So that's a good tipping point, maybe.
Well, so the ocean is part of the solution, certainly, because the ocean also captures a lot of CO2. So most of our emissions actually end up in the deep ocean, and also in the future, once we stop emitting, the ocean will help to take up CO2 out of the atmosphere that is already in there. So.
The ocean is always looking for equilibrium. So because the concentration is so high, the ocean can work harder. That's what I mean.
The ocean.
That's what they say. It will take more CO2 now.
That is true. That is what's happening. So if there wouldn't be an ocean, the concentration in the atmosphere would be much, much higher. So the ocean is actually taking up 90% of the heat, 90% of the carbon. So there is already a lot going there. Unfortunately, not all of it. But yeah, in the future, the ocean is certainly part of the solution as well. So it will actually remove carbon and also heat of the atmosphere.
Where do you personally think is like the biggest lever to stop carbon emissions? Is it like political innovation, or is it in technology? Does it start with individual behavior?
Yeah, well, so that is not my field, to be honest. So I only have a personal opinion on that. And yeah, I see it's very hard. It's difficult. And I don't have a straightforward answer to that. I mean, I flew to a conference last week because I thought it was necessary, and people start to commute again. So it's, I really don't know. I think that we shouldn't rely too much on the hope that technology will solve it for us. But I think we really have to think about yeah, how to live, what to actually strive for, what in terms of values, what do you actually want, what do you need, and yeah, sometimes maybe a little bit less of everything makes you equally happy. But it's a difficult, that's more a political discussion, of course. Yeah.
Would you think it would help if people have a better sense for deep time? Because I have the feeling we evolve not to think in deep time too much.
Yeah, it's yeah. So it is very different timescales. So humans are on the planet, modern humans. Our species is on the planet for 200,000 years. So if you think about processes that happen on millions of years, it's kind of pretty abstract. That happened in the past are not necessarily something that you can translate directly into what is happening in the future, but it helps us, of course, to understand how the climate system works in general.
What the hope is that many sectors and countries want to go to net zero in 2050. And the idea that you can have zero emissions, that's very attractive. And it helps technology development. Years ago, it was not, people didn't believe that get to zero. But now more and more, we think it's possible. Energy industry takes a little bit more time. But you need to make plans to get to zero. It's what many people really attract, to get innovation, and that can also go pretty fast.
Yeah.
So that keeps me hopeful. And then, of course, or taking CO2 from the atmosphere more and more. The geoengineering, which you were mentioning, but the safe ones are also effective. Methane, so
Yeah.
awful guy, of course, I do that. So there are ways
On the other hand, that people are pretty much okay to stand in line at Schiphol Airport for 3 hours just to go to a beach.
That's it. That's part of the
It's not
behavior.
over, I understand, and it's
Are
not
you
right.
sort of, well, doing this work, are you sort of getting anxious, or are you sort of being
No, well. No, yeah, so, no, I think, yeah, it's a little bit hypocrite indeed. You have to be, as a human being, I mean, you see that you see that also with Corona, but with climate change. You know these things, but you still carry on, of course, with your life. So what gives me hope is that it's still possible, right? It's not like that comment, if you've seen, that's really nice, what is it called, Don't Look Up. It's really good film, I think, about this comment that's coming towards us, and they're trying to warn everyone, and no one is listening. I mean, it's really a situation where you can't do anything anymore. Or maybe in the film they could have done anyhow. In this case, it's technologically possible. You know, we even have the narratives that tell us if we go this way, we can do it, right? It's really just a question of, does everyone want to...
Yesterday, the climate youth in the Netherlands presented a new plan. They say, well, we don't want to fly anymore, we want to eat more plant-based. And then we can get to zero in 2040 in the Netherlands. That's what they hope for.
Yeah.
So, yeah, I have a high hope in the youth. They don't buy cars anymore. They want to fly maybe, but very cautious. So, yeah, it's...
And it's also a step by, so what we are also trying, for example, in our lab to improve our carbon footprint. So we look at different things. So one of the points we note, actually one of the analysts, they notice, well, actually in our whole lab building, we still have the old light bulbs, sort of 40 watts.
That's the only
1,751 of, what was it, 1,750 of them. So you calculate, if we exchange all of those, replace them with LED, well, yeah, we save something like 80,000 kilowatt hours per year, or 30,000 euros per year with the energy prices. So there's a lot of easy things you can do, right? And that have also big impact. And it's kind of doing that step by step every year again and again. And hopefully we will get then to net zero at some point.
Yeah, I think we're getting to the last questions, maybe one or two. Marcel, do you want to have the last one?
I can provide 2 questions.
No,
I was thinking, what is your motivation for doing the work you do, and is it different for see some sort of mind shift or no mind shift at all on why you do what you do?
Well, so when I got into, so I didn't get into this, to be honest, because to study future climate change. I mean, it's obviously it's of use, but to me it's a really personal interest. So just the fact that you can reconstruct temperatures in the past was for me so mind-blowing, using those little forums and using that is enough motivation for me. I just like to see the data and think about it. For the students, it varies a lot. It varies a lot. So
No, it's okay.
there's of course a lot of students that are really interested in this topic. There's other students who just also want to explore the world and understand how it actually works. So it varies widely among the population. Yeah.
Last question
Yeah,
from a young
last question.
guy.
Yep.
Yeah. Like in all of this, where could creatives help? Because personally, for example, I remember this
IPCC, yeah.
report.
Mm-hmm.
I think this draw also some like public attention.
Yeah.
And I think I tuned into the live presentation of it. And I think what you did, for example, today, also kind of the design of the slides and so on, was like 100 times better what they did because it was like extremely boring and all the design. And at the moment, I also felt like, oh, they could need some help maybe also from creatives. Do you think like that creatives could also?
Yeah, absolutely. I mean, this is what if you think about these pathways, that's part. This is how you design your everyday life, right? So you basically think about ways to make it joyful without having a big carbon footprint. And it's not just about designing slides, I guess. It's really about designing a city, how to get from A to B, and it needs a lot of creativity, I think, to create a world that brings more happiness, essentially, to everyone, without the need to stand in a line for 6 hours and fly to an overcrowded beach.
But your suggestion is more like, how can we make it also more accessible?
In terms of outreach, yeah,
Understand
yes, yeah,
and
yeah.
to communicate it
Yeah.
to a broader,
Yeah.
to activate people
Yeah.
by communicating it in an easier way,
Absolutely,
in
yeah,
a more attractive way,
Yeah.
and to make it
Yeah.
also more attractive
Yeah.
to,
Yeah. Yeah.
to do your
Yeah.
part of that.
yeah. So yeah, I was working together with, and I forgot his name now. Too bad. Maybe some of you know, but a graphic designer who kind of worked on for NWO for a journal to kind of translate one of our papers that appeared 2 years ago and make it really sort of accessible, but also with really nice graphics. So he's put a lot of work into that, and certainly that also helps in science communication in general, right? So.
There's a lot of these great videos where you see the planet and from the past you see him heating up. You see it moving
Yeah,
in the heat.
yeah,
That's amazing.
yeah.
And I think artists at the moment are very important because we know a lot, but it doesn't move us.
Yeah, like the warming stripes that you see. So it's these images that really help you to.
But also to make the change attractive.
Yeah.
Design, how it looks.
Exactly.
Like.
Yeah. Yeah.
Yeah, that's now the time for
Yeah.
artists.
Yeah.
Science we know so much,
Yeah.
but there's no way.
I think that. This is not my, but I think Le Corbusier, for example, he was sort of designing the image of the city that is dominated by cars, right? This was his vision, basically. What does the future look like? And now we basically have to do it the other way around again. So what does the...
Okay, I think we can sort of go on for
Well,
hours now.
Yeah.
the worrying part as far as creatives is concerned is that there are so little of us here today.
Yeah.
Yeah.
Was it the first time here?
No, no, no.
No, okay.
So that's a different challenge for us.
So
Yeah.
As creatives, I think
Yeah.
to be
Yeah.
more aware of topics like this.
Spread the word.
Yeah,
Yeah.
well, but we're going to end it now.
Yeah, anyway.
And everybody can talk later. Thank you very much.
Beer. Thanks a lot. Yeah,
So,
that's welcome.
To sort of enjoy the positive sides of life.
Exactly, exactly.
Yeah, thank you very much.
Thanks. Thank you.